Hello everyone, welcome to my video. I am Dr. Sathyanarayan Rao, and today we will examine the mathematical foundations of planetary motions, specifically Kepler's law, and also see how we can solve planetary orbital motion using Newton's second law, using numerical methods in Python. And before Kepler's contribution in Europe, the prominent theory actually placed Earth in the center of the universe, with Sun and other things like Moon and other things were going around the Earth. And Kepler was working with an astronomer called as Tycho Brahe, who actually was measuring the movement of celestial objects. Before Tycho's time, there was an uncertainty of how we can measure the angular velocity of a celestial body with an uncertainty that was at the size of a moon, and Tycho reduced this uncertainty by his mechanical measurement tools like mechanical instruments. He reduced this uncertainty by a factor of 10 to 15 times. And this was a breakthrough at those times. Even after getting accurate data, Tycho himself never abandoned the geocentric theory, and he proposed a hybrid system where planet orbited the Sun, but Sun also orbited the Earth. But it was Kepler who was actually working with Tycho as his assistant, who made the important discovery that the planets actually go around the Sun in elliptical orbits, and it's the famous Kepler's three laws of motion. It's also like Kepler didn't come about this theory immediately. He initially tested about 70 different mathematical models before actually discovering that planets move in elliptical orbits. Interestingly, the idea of Sun being at the center of the planetary system is not a new idea. Ancient cultures, including some Indian philosophical traditions, actually hinted that Sun was at the center. For example, there is a ritual of going around something called as Navagraha, which means 9 planets, and if you closely observe, the Sun is actually at the center of different planets. Now coming back to the Europe, after Kepler's formulation of 3 different laws based on Tycho's data, actually Newton later gave the physical explanation of how planets move and why they move this way through his equation that is very well known as the gravitational force is equal to the gravity times 2 masses. So now that we have learned about the Kepler and how Tycho Brahe's data inspired Kepler to actually prove that Sun was at the center of our solar system, Kepler's laws actually inspired Newton to formulate his law of gravitation. And in our simulation, we will use Newton's law for simulating the planetary motion around the Sun, and this equation tells us that if we have 2 objects with mass m1 and m2, or capital M and small m, they will naturally attract each other due to gravity, and essentially they actually pull towards each other with a force that is proportional to r square, and that's the inverse of the distance between them. Since we operate in vectors, the r square becomes r cube. And why we need vectors is that the r square, while it gives us the how strength the gravitational pull is, when we multiply by the position vector, we get r cube, which helps us to calculate its direction. And so because force is a vector, we represent in this way r cube. And so with the Newton's equation, we can start with our code, and I'm going to explain the code that we are going to use it to actually solve the Newton's equation for the planetary motion. And first we are going to import all the essential libraries like NumPy and SciPy integrate, which is the main function that we are going to numerically use to solve the differential equation. We have also set up few constants like the gravitation constant and the mass of the sun with the distance and other units. And we will define a class for the planet so that we can organize the planet's data in a better way, which will help us in easily adding multiple planets and manage their initial positions and velocity. And so we have a planet class with initial positions of x and y with the initial velocity, and we can define different planets in this way if we have a class associated with a planet. So as a second step, we have to define our orbital equations. And so here we have the force equation with a vector form. In my earlier video where I solved Duffing's equation, actually I solved the same Newton's equation but for a different application to demonstrate nonlinear behavior of a oscillator. So where I explain why we need to break down equation into first order differential equation, because SciPy's IVP solver, which we will be using in the next slide, can handle only first order differential equations. So to work within these limitations, we split the motion of the planet into two parts. While one equation tracks the position that is linked to the velocity, the other equation will track the velocity that is linked to the acceleration. And on the right hand side we define a function that actually defines the equations that we are going to input to the SciPy's IVP solver that will take these two first order differential equations which we have defined here which includes the position x and y is the position of the planet, and also Vx and Vy are the velocity of the planet, and these are called as the state variables. And it's a common practice to split while solving the Newtonian mechanics, it's common practice to split into two first order differential equations like this. So it's exactly the same equation here is defined in this function. And the simulation time is set to 2 years here in the simulation time, and we get this number because there are approximately 31 million seconds in 1 year, and so our time unit is in seconds. And you see that we multiply by 12 to see the multiple orbits of both Sun and the Mars here. Earth and the Mars. So we will have two planets, Earth and the Mars, and simulate it. And the number of time step is set to 500, which determines how many points we will calculate along each planet's orbit. Like, think of it like taking 500 snapshots of where the planet is during the journey. We chose 500 as a balance, enough points to make the animation smooth, but also the simulation should be not too slow. So it's just we can play with this number. And T-span is simply telling the solver that what is the start and the end of the simulation. And finally T-eval creates an array of 500 evenly spaced time points between 0 and the simulation time with the number of time steps. So with our equation being now set up, we now move to solving them using the SciPy's numerical integration, which actually uses Runge-Kutta method, which also has adaptive step sizes, and we can also define the tolerances in the absolute and relative tolerances. And here we have the initial conditions for Earth and the Mars. So we are going to simulate two planets. And the basic definition of SciPy's equation is we define the first order differential equation as a function of t, y, where y is the state variables here. And so first I create an empty list where we will store the results of each planet, the orbital points, and we also initialize the maximum radius to help with setting the visualization limit later, because as planet moves the axis can change, so we want to fix the axis to the maximum radius the planets can take. And we also define the initial conditions here for the planet, and the planet is actually defined as it has its own class, as we discussed earlier, and I will share the complete code in the description below. And so here I am explaining step by step, and this is the part where we are solving the SciPy's numerical integration. And after we define the initial condition, here I call the solve IVP function, which is the main function that actually solves the orbital equations here. And here we pass the t-span, initial conditions, and other variables as inputs. And after we solve the equation, I'm actually I store the each results in a list called solutions here. We initialized here as an empty, and we append it inside the loop, time loop. And with this setup we have created the framework to simulate and capture each planet's motion that can be visualized with an animation that we will see in the next step. So now after we have set up our SciPy and other equations, we can finally visualize our setup. So first I create a figure window here with equal aspect ratio, because we want a circular orbit here, and then we scale the x and y axis based on the maximum radius that we computed in the previous slide. And we will add some grids, and this is it's just plotting our with sun as the fixed location at 0, 0. We compute the planet's orbit and plot it. We plot the planet's position as well as the velocity. And these paths are created here. Alpha equal to 0.3 means these paths are created with little bit of transparency to see the overlapping orbits, so that we know that the planet takes same path in the next iteration. And finally, in the final slide, we actually we write the animation as an MP4 file using FFmpeg writer library, where we define what frame rate and what bit rate, and finally we write our animation in orbital motion.mp4. This writer grab frame actually is each frame is captured here, building our animation frame by frame. And so I also update the title here. Everything within this loop is being updated. And so we will run this code and see what we can get now. So here is the complete code we have set up here, where here at the final we store the orbital motion as a MP4 file. And let's run this code and see what we get. And you can see the FFmpeg file is writing our frame by frame the animation file, and we see that the result animation is saved, and we can run the file and see what we get here. And you see here, so finally we have implemented the planetary motion, and we see the Earth and the Mars revolving around the Sun. This is how planet moves by solving Newton's equation. And so I will be sharing this code in the GitHub repository in the description below, as well as a MATLAB version. I have uploaded them in the file exchange, so please feel free to check them. And thank you again for watching this video. I will come up with some different video in the near future. Thank you again.